Okay, this is the third video from Chapter 5, and we're talking about optical fibers in Chapter 5. And in this video I'll talk about step index fiber modes. And what we're going to do is we're going to make use of our understanding of the mode diagram from Chapter 4 for the slab in understanding the modes for step index fibers. The main difference here is that we are in a cylindrical geometry now. And so we always have the symmetric case. You'll recall that for the slab we had the symmetric slab and the asymmetric slab. We're always in the symmetric case. And so our mode diagram is still going to range from N2 up to N1, where N1 is the index of the core, N2 is the index of the cladding. And I'm going to make this mode diagram and draw that the first mode really does start at 0 here, consistent with the fact that it's a symmetric type of geometry. And then various other modes come up very much like in the slab geometry. However, it turns out that the mode diagram is complicated by multiple types of modes, and so we get a bunch of different mode curves here. And this is sort of schematic at this point. The next thing I'm going to do is I'm going to label this horizontal axis with the variable v. And you'll recall that for the slab we labeled this d divided by lambda for the slab, whereas here we're going to call it v, and v is called the normalized frequency. And the fact that it's a frequency is consistent with the fact that it's proportional to 1 over the wavelength, and it's going to be 2 pi a over lambda square root of n1 squared minus n2 squared, where a is equal to the core core radius or core diameter. Yikes. Hold on for 1 second. I tend to take it for granted that it is the core radius, but I want to check that. Yes, it's the core radius. Okay, and so you can see that V is a lot like our recall from our slab. Recall from the slab waveguide that we used d by lambda for the horizontal axis. So this is a lot like d over lambda, except it's a over lambda, and it has a 2 pi and a square root of n1 minus n1 squared minus n2 squared. And in fact, that quantity is the numerical aperture, so this is 2 pi a over lambda times na. Okay, and it turns out that you can use this variable and have a single plot that works for all step index fibers with core index n1 and cladding index n2. Okay. Now the most important value that the normalized frequency takes on is roughly 2.4, which is the cutoff to single mode behavior. Okay, so if v is larger than 2.4, that is if either a, the core radius gets too large relative to lambda, or lambda gets too small relative to the core radius, then it will take v past 2.4 and we will have multi-mode behavior. So we're interested in single mode operation, and single mode fiber implies that we want v to be less than 2.4. Okay, if we want to have good confinement, we want V larger than 2.0 for good confinement. I've shown a couple slides on mode confinement. And if V is greater than 2.0, then we've got more or less good confinement and lower loss. Okay. Now, what are all these various modes? Well, these are labeled. Let me show you. Well, let me label a couple of these. This is called the HE11 mode. That is the lowest order mode, and that is the mode that we use. The HE11 mode for single mode behavior. There's a bunch of other modes. There's the HE21, the TE01, etc. Lots of modes. So we've got the HE variety, we've got the TE variety, we've got the TM variety, we've got the EH variety, and these have various geometries. And what I'll do is I'll show you the actual mode diagram. First, I think I have a copy here that's a little bit larger than the one in your textbook, but figure 5.17 in your text is this one. This is the N from the cladding index up to the core index, starting from 0, and this shows that the normalized frequency is going from 0 to 6 in this diagram. You can see the 2.4 for the cutoff for single mode behavior, and you can see the various labels. There's all kinds of modes in here. What's really cool is the symmetries that these modes take on. And this diagram shows you a whole bunch of different mode profile plots, showing you that a lot of these different modes have all kinds of interesting, beautiful mode patterns. And these are mode profile plots. And so it's the circular ones that could represent, say, this one in the upper left-hand corner, just concentric circles represents essentially the Gaussian index profile. So the HE11 mode is that beautiful mode that we're after with the Gaussian profile. And this Gaussian profile will give rise to this circular mode profile geometry. Okay? And you know, we say that this is single mode behavior when V is less than 2.4, so but it's important to realize that there are two polarizations possible. So even though we say it's single mode behavior, technically there are two modes, one for each of the TE and the TM polarization. Okay? And so that's the basic idea. The H's are the H's stand for hybrids. We've got the TE and the TM, you know, various polarizations. I don't think it's really worth trying to figure out all these different modes from a geometry perspective. Maybe I'll go ahead and take this HE11 mode and try to draw it as a sort of a perspective of drawing so that it is circularly symmetric with this Gaussian profile. And I can draw the Gaussian profile in the other direction also. And that's where these circular mode contours come from. Okay, so those are those circles. I think I'll end this video here and we'll pick up with the next video. Thanks.